and researcher and education in Divinity Chapel. So before starting the session, let me introduce Dr. Maipal Jadeja sir. Dr. Maipal Jadeja received his PhD degree from Dhirubhai Ambani Institute of Information and Communication Technology in the field of theoretical computer science. He currently works at MNIT Jaipur as an assistant professor. His research interests include theoretical computer science, social network and network analysis, machine learning on graphs, and generative AI in education. He has published several journal articles, book chapters, and a reference book in these domains. His research work is presented at reputed international conferences, including GSB CIJR 2015 and 2016, SCI ICTIR 2017, and ICWE 2023. He has supervised 3 PhD students, 12 MTech students, and currently he supervised 4 PhD students and 3 MTech students. On his YouTube channel, CS Simplified, he has uploaded more than 150 videos. So to date, the channel has received more than 3.5 lakh views. He has also developed a massive open online course on Python programming, the MOOC course, which has attracted over 1,500 learners and boasts an impressive average rating of 4.8 out of 5. Dr. Maipal Jadeja has delivered numerous expert talks at prestigious venues, including a session on AI-powered advancements in education, organized by Dr. Priya Ravi from Massachusetts Institute of Technology. The top-ranked institute of the world is Quartz 21 since 2012. He is the creator of Python to Pathshala, a custom GPT feature by OpenAI that enables bilingual Python learning with dynamic examples, contextual applications, and intuitive metaphors. He is also a collaborator of the AI modification at Oxford University's initiative, contributing to global efforts in promoting ethical and research informed use of AI in education. So, thank you, sir. Thank you for coming, accepting our invitation.
Thank you so much, sir, for my detailed introduction. So now I guess we can start the session. Hopefully my screen is visible. I can also see it, but still, in case of any issue with respect to my screen or voice, please let me know, even in between the session. Otherwise, we can start now.
Sir, it is visible, sir. Your voice is audible, sir.
Okay, sure. Thank you. So usually, okay, so the good news about deep learning on graphs, or there are many words of this particular topic. Like before we start, I would just like to mention some of the names so that you understand what we are going to learn today about. Right. So there are multiple ways to look at into graph neural networks, right? And the form which I usually consider this particular topic is it's simply deep learning on graphs. So I just I have just attended last couple of minutes of Dr. Vikash sir's session, and he was mentioning about activation functions, including sigmoid and I guess softmax. So the good news is, with respect to all the participants, is whatever concepts you have learned so far in this particular FTP related to deep learning, all those concepts will be useful, right? All the hyperparameters, like including or dropout, or concepts of epochs, right? So on and so forth, right? So the fundamental ideas, especially with respect to implementation part, will remain as it is. Of course, the architecture is significantly different. Therefore, the technology is new, right? So therefore, it's called graph neural network. It's not just normal deep learning. It's deep learning on graphs. many researchers also refer to this particular kind of a domain of research as nothing but machine learning on graphs, or some also say geometric deep learning, right? So all of this terms refer to the single entity, which is nothing but graph neural networks, on which we are going to talk about today. So basically I have 2 hours. So what I will try to do is in the first hour, right, in today's session, especially I will focus on some fundamentals, right? For now, you may see that these things are slightly irrelevant, but once my second session will be over, you will be able to connect the dots very easily, right? So what I would like to do for now is I will start with some questions, and then we'll see how answers of these questions are kind of interestingly aligned with architecture of graph neural network. And again, since this is FTP, so most of the participants are faculty members. So I assume that in future you will also kind of pursue this domain, right? You may pursue this particular domain as nothing but your domain of research also. So therefore, my talk will be aligned like that. I will also try to give you some kind of fundamental ideas based on which you will be able to kind of build something of your own. Because if I just talk about normal architecture and its implementation, then it's quite straightforward and anyone can do it. And there are many resources available online also using which you can do it. But the key idea is why this particular architecture works. That if you know, then only you will be able to kind of modify that particular underlying architecture, right? So that's a motivation. So that will be the idea of that will be the flow of these 2 talks. Okay. So without wasting time, let's start. So the very first question, right, which I am going to ask you today is, according to you, how small is the word, right? And we often say this, right? The word is too small. We refer to this particular phrase many times. Most of the times, it's with respect to transportation, right? We go sometimes we go to airport, and then of course we just go there and come back. We take flights and go to some other cities, and then we say nowadays it's so easy to reach from point A to point B, irrespective of where those 2 points are in the world, right? And then we say world is so small. And sometimes, let's say we are talking with our friends, and surprisingly, we mention a particular person, let's say person Y, and then your friend also kind of know that particular person, and surprisingly, you say, "Oh, how do you know that particular person? Why he or she is my friend, right?" And then we say, "Oh, world is so small, right?" And there can be other instances also, but at least in these two, commonly we say that word is becoming small like that. But now my question is, can you mathematically quantify that how small the word is actually, right? So let me go to this whiteboard and let me give you some options, and you can just pick your answer in nothing but comment, right? So one claim can be, let's say it's 1 lakh. Like 1 lakh is very small with respect to total population of world, which is in right billions, right? So one possibility is, let's say 1 lakh. Second one is, let's say I'm saying not, it's not 1 lakh, it's just 10,000. Third one, let's say I'm saying it's not even 10,000, it's 1,000. And fourth one is I am saying it's even more, less than that, is not even 100, it's in this particular range, 4 to 10, right? So what is your kind of prediction, right? You can write your answer in the chat box. What do you think? Any guesses? Option A, B, C, D. So Dr. VB Nikamji has already answered. It's I assume that it's I have pronounced name correctly. Six hop. Okay. Depends on the presentation. That is one more answer. Okay. Option A is kind of so far only one answer we have got, which is nothing but option A. Any other answers? So if we don't, okay, option C, okay, fine. So, if we just see this, then it seems all answers are possible, right? And I can also add some few more zeros, and then someone can say even that answer is also correct, right? 10,000. Most of the people are saying 10,000, right? Okay, so now we can't guess. Okay, so it's good that we have guessed it, of course, but we can't validate this without any experimentation, right? And fortunately for us, the experimentation part has already been done. So let me go. Let me walk you through that particular experimentation, and then we'll come back again, right? So the famous experiment, just to identify how small the word is with respect to kind of one can say friendship network. Right? So what's the idea of friendship? If I know a particular person, then we assume that I'm connected with that particular person. Just like you can assume Facebook, but Facebook is kind of virtual social network. Think about your real social connection, right? So how this particular experiment kind of try to identify how strongly humans are connected, right, on physical actual network. That's the idea of this particular experiment. So let's try to understand. Experiment is quite straightforward. 296 random people were kind of okay. So before even I talk about this experiment, I must give you one more example so that you can kind of relate with this more. So the idea was like this. Let's say if I again rephrase the question, then let's say this is you, and now I tell you to connect with one particular person who is in, let's say, Nigeria, right? Okay. Ignore whether the spelling is correct or not, but let's some African country is there, and I tell you to connect with this particular person. Let's say the name of the person is PY. Okay. And now the idea is you don't know this particular person for sure, right? If no, then if you know, then we will say that distance between you two is nothing but just one. But what you will do usually, since you don't know, what you can do is you try to connect with someone who works at, let's say, at Delhi in foreign ministry, right? If you can connect with this particular powerful person who is sitting at Delhi and he works in kind of foreign ministry, then it's very likely that with the help of this particular foreign ministry guy, we can contact this particular person. So now, what you will do, you will try to contact some influential person in your state, or maybe you via so right, you will try to instead of first step, you will ask this particular question. I don't know this particular target person, but as compared to me, which one of my friend has more likelihood to know this particular person from Nigeria? It may be the case that you're one of your student is from, let's say, directly from Africa. In that particular case, you can directly contact to that particular student, and student can connect with some African university, and then so on and so forth. You can directly reach to that particular person. And in the second path, if we are going to some ministerial guide, then also we can reach to the final person. So we try to replicate the same kind of thing in actual experimentation. This is just idea. Let's say after to eight iteration, right? We could reach to this particular person via whatever message was there, and it was received by, let's say, person V PY after, let's say, 12 intermediate. Then we will say the distance between these two is nothing but 12. But this was just one experiment. The question is even bigger. You can imagine what will how many different combinations will be there, even if we consider that the, let's say, world has only 1,000 people, right? Then also we have to do a lot of experimentation, precisely 1,000 choose 2, right? So if you try to figure out this number, then it will be roughly 10 raised to 6. This many experiments will be required to figure out what's the average uh, kind of path length, or what's the distance between on an average between two people on Earth, right? So it's a very kind of challenging question. It's not that straightforward, because here I have selected a particular person like me and some African person, but in general we are talking about. So it's not about like you can also kind of select some illiterate people. You can also kind of select some introvert people. You can also select a person who is right, extremely famous, like our prime minister, right? So on and so forth, right? So there are many combinations. So what we are going to do is we are trying to averaging out, right? On an average, how far two people on the earth are, right? So now we can talk about this experimentation, and you will be able to relate very easily. So the idea was, instead of this many people, because we can't perform this experiment on the entire population of world, of course. So what Milgram did was he considered some sample size, let's say 296 people, but they were selected randomly from two different cities of USA, Nebraska and Boston. And then the idea was simple: letter was given to them, and the letter must be sent to a particular stockbroker who lives in Boston. Okay, and then the idea was they wanted to calculate what's the in how many intermediate individuals the letter will be reached to the final destination, which is nothing but the stockbroker, right? So the rules are pretty straightforward, as you can see. If you know the target person, then forward it, right? That's rule number three. If you don't know, then instead of you consider or forward the letter to one of your friends who has more likelihood than you to know that particular target person. Likewise, you can continue, right? And they will attach a postcard in between just to keep track of how many intermediate kind of people were considered before the letter finally reached to the target person. And here are the results, right? So as you can see, right, and Dr. V.B. Nikamji has answered correctly, right? It's famously known as 6 degree of separation. And in this particular case, you can see this is not fixed number, it's average number. Right? It may be the case that some letters not even received. As you can see, the sample size is 16 over here. So whereas initially we had started with, if you can remember, 296. So it's not saying that for all 296 letters, they will be going to reach to kind of destination with exactly 6 intermediate people. That's not what we are claiming. But as you can see, some numbers are you can see some numbers are over here also. Some are here also, right? There is one there are kind of we can see that there exists at least one letter which took 10 intermediate people, right? But you can see peaks are over here, right? And 4 and at 6. And if we consider average, then it's around 5.2. So now this is how people are communicating, one can say. Now we are not going to ask this particular question why it's happening, because that is beyond our understanding. It's a kind of nature's language, right? We can't we can just decrypt it. We can't kind of um, get intuition why it's happening, correct? Okay, fine. So now this was fine, that this is how people talk or people kind of connect with each other in real world, one can say. But the amazing thing is this particular pattern is consistent not just with respect to human interactions, even with respect to interactions among mathematicians, right? So now we are talking about the famous mathematician of 20th century was known as Ildos, right? And Ildos had kind of he had spent his entire life in kind of towards research and giving expert talks. He didn't even buy his own home because most of the times he was kind of traveling for work purposes. So now, if we try to see, right, how Ildos was kind of writing papers. And what's the idea over here? Let's say I have written a paper with collaborator of Ildos. So then I can say I am a good mathematician because collaborator of Ildos has had kind of preferred me to work with him, right? So that will kind of communicate the or showcase my status in terms of mathematician, right? So if your Ildos number is less, that means you are good because you are very close to Ildos work, right? So let me give you one example, then you will be able to relate with this. So for example, if we take example of Einstein, then we can say Einstein's Ildos number is 2 because Einstein had worked with this particular Gabor Strauss, and Gabor had directly worked with Ildos via this particular paper, right? So this is, we are talking in terms of publication, not in terms of like informal communication. The previous Milgram's experiment was with respect to informal communication. Here we are talking about formally with respect to research papers, how people are or how mathematicians are connected, right? So now if you see, then this is nothing but kind of graph of mathematician where in the center, of course, Ildos is there, and Ildos number for Ildos is of course 0. And then if collaborators of Ildos, right, if co-authors, all the co-authors will be at distance 1, right, union of co-authors, and then so on and so forth, right? So now you got the idea. I'm not going into the details, but the summary part is important. Even in this particular case, if you try to find out what's the kind of mean Ildos number for mathematician, then it's again 4.65. And even if we go further, right, so it's surprising that how people are kind of informally communicating in real life. The same kind of property is kind of we can see even in formal setup with respect to mathematicians, how they are collaborating, right? So it's very surprising. And not only this, this will occur many times when we talk about graph neural network or any of the network, right? So if you even talk beyond human lives physically, that even if we go inside human body and if we try to kind of design protein interactions, right, with the help of biology graph of human, that or body graph of humans, then also we observe the same phenomena, that the average distance between protein cells is again in this particular range, right, which is fascinating. Okay, fine. So now this was the first property, first question, and I have answered it correctly. Now let's go to the second and third question, and then quickly, of course, fourth question, and then we'll formally start a graph neural network, and then of course we will also answer why these questions and why, especially apart from questions, why these answers or justifications are helpful for us in order to design architecture of graph neural network. Okay, so the second question is again interesting question. Think about your top five friends of real life. Okay, so instead of five, let me just go with three. So let's assume that this is your friend one, this is your friend two, this is your friend three, and this is you. Okay, so now what I would like to do is I would like to quantify a particular parameter which will showcase how closely your friends are connected with each other. So it may be the case that these two are your college friends and they are also friends with each other. So whenever is any relation between my friends exists, of course I'm talking about friendship relation, then I will use this particular blue line. So now the question is, how many uh, blue lines you imagine in your neighborhood, right? So in this particular case, it's obvious that maximum three choose two blue lines can occur. Why? Because there are three friends and I can choose any two of them and then connect them. It may be the case that all these three friends are from your college and you had very close group, and therefore all of them are kind of connected with each other and they are also very good friends. Friend one is also instead of F, I should use P. Let's say person one is friend with person two, and person two is friend with person three also, and person three is also friend with person one. Right. So out of this, all possible blue lines, in this particular case, all are present. So I will just say 3 choose 2 divided by 3 choose 2, and then I will say the quantity is nothing but 1, or 100% of my neighborhood is connected, right? Now, there can be some other scenario also, right? This is not the case for kind of global case. It may be the case that your one friend is from your school life, right? This is again you. This is your first friend, which is kind of your school friend. Let me call P1 dash. Your second good close friend from your, let's say, college life, and third good uh, close friend, let's say, from workplace, right? And now this is the case. So in this particular case, again, number of blue lines possible are 3 choose 2, right? But none of them are present because they are kind of coming from different geographical as well as kind of physical locations. Geographical and physical are same. So sorry, geographical location as well as, and some reasons, let's say you they don't know, right? One another, right? P1 dash, P2 dash, and P3 dash. So we'll say 0. So that means this quantity can be anywhere between 0 and 1, right? 0 means 0% of your friends are kind of connected, right? Or know each one another. 1 means 100% of your friend kind of know uh, uh, one another. So what do you think, right? Towards which side this number will go? Should I say it's towards 100, or should I say it's 0? Okay, and before that, before I kind of complete my question, you have to imagine this number will increase significantly. This is a very toy example because only I had considered three friends. But in your case, right, depending upon how popular you are, that is again the next question. But let's imagine that you have 25 friends. Then imagine how big this particular number will be. It will be 10, 25 choose 2, right? So you have to kind of evaluate all this kind of more than precisely, let's if we say then 300 different kind of possibilities you have to explore. Now, out of 300, how many are actually present? You have to tell this number. Yes. So now, what is your guess? I'm not quantifying this for now. What do you feel? Whether will this number is high or low in your case? You can just type H or L. H stands for high, L stands for low. What do you feel? Neighborhood. how many of your friends are also friend with one another, right? So it's very likely that they also form a group, or it's very unlikely that they will form a group. What do you feel? Okay, Preeti ji is saying hi. Okay, any other answers? Okay, fine. So we don't have very, I can say, much time. So I'm not spending more time on waiting. But the answer is correct. Actually, in for real world networks, or we will see, or graphs, we'll see that this quantity is actually high, right? Many of your friends are also friends with one another. And then the third question is, of course, related to popularity. Uh, and I'm not discussing this in detail, but I'm just giving you direct intuition and answer. So now I will just give you one example, and then you will be able to relate this with this very easily. You can guess, you in your on your phone you have many apps, right? I can imagine that you will be having at least 50 apps on your phone. But out of those 50 apps, how many apps you are using on daily basis? Those apps are very less. I can guess those apps are only four or five, like WhatsApp, Instagram, nowadays, ChatGPT, right? Maybe LinkedIn, right? We are professionals, right? So those four or five apps only we are going to use most of the times. So can we say that the extremely popular apps are very less? Do you agree? Similarly, less popular apps will be also very less, because if app is not running, not a lot of people are downloading it, then it will be kind of gone from the app store itself. All right, so similarly I can easily say that in terms of graph, if we try to relate this, then number of points with high degree will be very less, and number of points with very low degree will be also very less. Most of the points will fall in averagely popular category, and this is true, right? If you can't relate with this app example, you can take example of Facebook or Instagram, right? Most of the people on Facebook, right, they are not extremely popular, we know, right? They will have right, friends ranging from 100 to 5,000 or maybe 10,000. But influencers or celebrity or maybe leaders, right? Those kind of accounts are less as compared to rest of the population. And there will be some accounts which most of them are kind of fake, with very low number of kind of friends, because they will kind of randomly send requests to many people, and then suddenly people will report them and their account will be kind of closed. There can be some kind of introvert people who are on Facebook or maybe Instagram with less kind of followers or less friends, but that number is still very less, right, as compared to our second category, which is nothing but averagely popular, right? And the last question, right, you yourself has have answered this particular question, since you are attending this particular FDP even though it's in virtual mode, that itself showcase that you are part of a community, right? You are not an isolated person, right? So most of us are like that, right? We are social, right? We belong to a community, and of course, I'm giving you examples of people and us, and as well as researchers, mathematicians, so that we can relate with these concepts. These concepts are related with not only that the examples which of course, giving you, they are kind of fundamental questions of network science. And soon we will be able to see how these questions and answers are aligned with development of graph neural network, and how they can help us with respect to research as well as problem solving. Okay, fine. So with this motivation, I guess we are ready to formally talk about graph neural network, and also I can say deep learning on graphs, right? So the first question is, why graphs, right? Why do we need to even talk about any new topic, right? FTP, this is the fifth day of FTP. We have learned so many kind of deep learning models. Why one more model, right? So that question is valid, and one should ask this before we kind of formally talk about architecture and other things. So the idea is, if we talk about the traditional deep learning or machine learning, then it works like this. These are isolated points. Points may represent anything. They may represent data points or images or videos or anything. But we don't consider any kind of interactions or relations between these entities, right? That is kind of uh, state of art of deep learning or machine learning, except for graph neural network. But if we talk about graphs, then not only we will consider these data points, we'll also consider interactions or relation between these data points. And of course, like it's very obvious that if you have more information, then it's very likely that the results will improve, right? So consider the case where here also we are not discarding the information which had earlier. We are adding this extra bit of knowledge, which is nothing but interactions, and these interactions will help us with respect to better results, right? So that's the motivation, right? So instead of considering just points, we'll also consider interactions between these points. And the main idea, the key idea of graph neural net, or also its challenging thing, is how to come up with this graph, right? Because many times, like the examples which I have considered so far, like for example, Facebook or Instagram, in those cases, graphs were very trivial, right? Construction of graphs are pretty straightforward. That people we can represent with dots, and if they are connected on Facebook, then we'll put an age between them, and we get this kind of graph very easily. But that won't be the case every time, right? Imagine a scenario where I try to apply graph neural network for, let's say, identification of autism. So then I have a lot of MRI images. So MRI images I can represent as, let's say, dot. Okay, and whatever report properties are there, I will say they are features. But how to construct age, right? So then I have to come up with some measure. Like for example, I can have some similarity, like cosine similarity between different points, and if it is beyond some threshold, then I will put an edge. So likewise I can generate it, but then also I have to make sure, right, that whatever I am generating, it must be something sensible, because then only my model will work. So my entire focus is on of this, as well as the next talk will be how to ensure that we can kind of get best out of graph neural network, right? We are just not just seeing it for the sake of completion, but we will try to see how to design good input for our graph neural network, so that the output becomes kind of better than whatever the existing techniques are. And this is how that I won't spend too much time over here, but this is just to showcase you. It's not just about I must say mention social network analysis. It's not like that. Whatever we are going to talk about is applicable only on social networks. You can think of any domain. You will be able to see some kind of graph aligned with that particular domain. And if it's not there, you can generate of your own with sensible rules, and you can advance that particular field, right? So if I give you one more interesting example, then recently we had worked on a domain of architecture where floor plan was given to us, and the idea was how to automate the process of labels of those floor plans. So whenever we go to buy house, they usually show us this kind of floor plan, that this will be your kitchen, this will be your kind of bedroom, this will be washroom, so on and so forth. So how to let's say instead of that, let's say we have just floor plan, and our model will predict based on the kind of proximity of different portions of that particular underlying given nothing but our plan, and then model will tell us that this region must be kitchen, this region must be washroom, so on and so forth, right? So that was the idea, and we could achieve enhancement of around 15% in terms of accuracy as compared to state of the art other deep learning or machine learning methods, right? So it's not like that. So sometimes you can apply these concepts even to field which may not seem intuitive, right? Just by looking at it. Okay, fine. So as you can see, of course, there are many other networks, including social networks, citation network. We can even represent internet in terms of networks. A network of neurons. This neural network and neural network which you are learning, both are different. This is nothing but our actual brain cells, network of that. And Vikas sir and Surendra sir, both of them are talking about artificial neural network, right? So hopefully you understand the difference. And then you can there are some interesting works going on in the domain of computer vision also, where people are kind of applying concepts of graph neural network in scene graphs and so on and so forth, right? So and impact, as you can see, this many companies are kind of using concepts of graph neural network or network science in one or another way. For example, Google is Google mainly because of concept of PageRank algorithm, and the idea of PageRank is again represent the web pages in terms of nothing but graph, right? Facebook friendship recommendation, Amazon product recommendation, Pinterest again pins or images recommendation, right? And a lot of other companies, right? They are using this particular concept. Okay, so now before we talk about architecture and kind of other things, the important question will be, how do we take advantage of this relational structure for better prediction? Let's say the first part is somehow done. Let's say we have this graph now, and now how we can take advantage of this entire graph structure for completing some kind of task. Okay, so now we have to talk explicitly which task we are talking about. So the first task is called node classification. So what do we mean by we say node classification? Let's say node can represent anything. So let's talk about people one more time. So let's say what I'm doing for now is I'm analyzing tweets, and let's say election is coming, and I would like to identify whether the person will vote to party one or party two based on some tweets. Okay, so that is nothing but node classification, right? I'm trying to classify, right, what's the type of this particular person, right? So that's one example. On it's any kind of classification. Like for example, let's say in the case of brain network analysis, it can be whether the person has autism or not, right? Like that. Then second one is predict whether two nodes are linked or not. So it's called link prediction. Link is nothing but age, right? So it's what's the likelihood that for now there is no age between these two person, let's say X and Y. What's the likelihood that in future these two will be connected? It's a very domain, and even if you can enhance this by some magnitude, right? Companies will be very happy with you, right? Because they will welcome you, in fact, because this is everywhere, right? If you can enhance the YouTube kind of recommendation system, because that's what it's doing, right? This is the video which you are viewing right now, VX, and what's the likelihood that you will like video Y? And the same thing is there with respect to Amazon also, that you are buying a product VX, or maybe some set of products which you have already bought. Now, what's the likelihood that you will buy product Y in future, right? And you can pick any other example, right? So wherever marketing is there, this link prediction makes sense. One more interesting application is trivial example of link prediction is LinkedIn recommendation, I can say. Right? In LinkedIn, you get this kind of recommendation. You may know this particular person, or based on, they don't say you may know, but they say based on your recent activity, you may know this particular person, or based on your role, right? Based on your geographical location. If you are at Delhi, then they will recommend people around Delhi. If you are at Jaipur, then accordingly the recommendations will change. And also depending upon what things you have reacted, you may get certain type of recommendations of people, right, in the very first recommendation tab. So that is nothing but they have performed this. They have identified what are the possible links, and then they are just recommending. Or Facebook recommendation, that's similarly. Next one is community detection. So let's say you are introducing a one new product, right, which is not applicable to entire marketplace, but only a segment, right, belong to the, let's say, this particular age, then 20 to 30, right? So then you have to identify, right, which people belong to this particular age range, and then you market or you showcase your ad only to those people, right? So that is nothing but one kind of application of community detection. So first you are identifying like-minded dots, and then you can utilize that particular knowledge to accomplish some task, right? And then of course network similarity, that is also one more kind of application, right? So people also, like I mentioned, machine learning on graph or deep learning on graph. So both terms are interchangeably used, right? So complex domain have a rich relational structure, which can be represented as relational graph, which we have already seen. And by explicitly modeling relationship, we achieve better performance. So the second part is important because it's not that every time the relations are kind of implicit. Sometimes we have to model them, right? Which we have to explicitly model, right? But the trouble
Hello, sir.
is, yes. Any questions you can ask?
Sir, hello, sir. Actually, your laptop battery seems low, sir. 3%. It may get soon discharged. So
No
better
issue.
to
That is no, that is different device. No issues. I will share it from my system. Okay.
okay.
Uh, I'm using two devices actually. My iPad is also there, so I'm sharing via iPad. So once it's kind of low, even less than 3, I will share from my screen. No issues. Or if you
Okay.
want me to continue like this, then also it's possible. Just give me a minute in that case. Thank you. Just a second. Okay, meanwhile, I can continue what I was saying. I'm talking about, unfortunately, not everything can be represented in terms of graph, right? So, for example, many times we get this kind of data which is of regular in nature, right? For example, you can see this kind of images or text, and then we get beautiful matrices, and then we apply them using nothing but we apply the standard models of ANN or CNN. That thing we already know, right? But now the question is, right? How can we develop neural networks that are much more broadly applicable? Because so far, hopefully, you know about ANN and CNN. And we know that the idea is quite simple. Whatever metrics we have, what we are going to do with respect to that particular metrics, can anyone tell me? Let's say I give you the simplest data set, which is called Hello World of Machine Learning, which is nothing but the standard data set of MNIST. And now my question is, can anyone tell me what usually you do when you apply your normal ANN or CNN on this particular data set? Any just rough idea? Okay, classification is n tasks that you are going to classify whether the digit is 0, 1, 2, 3, up to 9. That is good. That's the final objective. That's the end result. But what's the process? I give you this images. First thing you do with respect to this images is, okay, so maybe what I can do is I can draw something, then you will be able to relate with this very easily. So let's say this is my matrix, and I would like to apply my normal ANN. So what you will do? For now, I'm skipping a lot of details, of course, because this is not ANN class. But do you agree that you will first flatten this, and after flattening, right, what will you get? You get this kind of vector, right? And then you will have a lot of entries into this, which represent nothing but pixel. And then each pixel you will give to one of the neural network like that. Okay. And then your model will complete the classification task. Do you agree? This is the process which you follow, right? Uh, of course, I have skipped a lot of details. Sorry for that, but I'm just explaining the parts which will be helpful for me with respect to graph neural network. So now the question is, can't we usually all of us are kind of lazy, right? And usually we don't kind of feel need of learning or designing anything new. So what is my proposal? Instead of using this normal matrix, which is my image matrix, let me call it IM. Can't I use my adjacency matrix, right? Because every graph can be represented with respect to adjacency matrix, right? It's again one matrix, square matrix, using which, and if let me explain it to you very easily. In just let me take this example. So let's say I want to represent this graph, okay, with the help of one matrix. Then what I will do? I will simply write ABCD over here. I will simply write ABCD over here, and then I need to, this information will tell me how many nodes are there. So I know that I have 4 nodes, and then I will just put 0, 1 just to showcase which nodes are connected with which other nodes. So for example, there are no self loops because nodes are not connected with selves, right? With themselves. So therefore, I can put straight away 0 over here. Then A is connected with B, A is connected with C, A is connected with D, and this is undirected graph. So I can copy these three elements over here. Okay. Then B is not connected with C, so therefore C is not connected with B. B is connected with D, no, so B is not connected with D. And then C is connected with D, yes, and D is connected with C, yes. So this is how I can get this adjacency matrix. Very straightforward. If there is a kind of connection between I comma j, then I will put 1. Otherwise, I will put 0. It's a very straightforward logic, and hopefully all of you know. But this is just to kind of recall you. Now the question is, my question is, can't I use AM instead of IM? And then I can say the topic is over, and I have concluded my talk in 45 minutes. Let's say. Right? Hopefully you got the idea, right? With respect to my question, right? What do you think? Answer is yes or no. What do you feel? Of course, I have to justify it. I can't ask justification, but what your intuition says for now? Can I replace IM with AM, and then that's what graph neural network does, or it's something else? What do you feel? You can just write. My question is AM. I can translate AM to my normal nothing but whatever AN model to. I can give this as my input, and then I get whatever answer, whatever task is there. Let's say classification. I can perform it, and I am done. So whether this particular path makes sense or not, what do you think? This replacement will work or not? Yes or no? Replacement will work. If you feel yes, then you can write Y. Otherwise, you can write N. What do you feel? Just we are changing. Instead of image matrix, I am proposing instead of image matrix, instead of image, just use this kind of nothing but our graph matrix, which is nothing but adjacency matrix, right? Okay, so I've got couple of more than two responses. So 3 of you are saying that it will work. Okay, so let's see. Okay, I'm not giving you answer directly. Okay, let me kind of explain you something, and then we'll come to the answer. Of course. Okay, fine. So as you can see, of course, I'm not talking about recent years, but even if you see the first 3 years after introduction of graph neural network, it was the first paper of this particular domain came in 2017, and you can see rapid kind of increase in this particular field in terms of number of papers also in reputed journals, right? So the question which I asked you just now, right? We can kind of write this particular question in terms of if I want to represent this particular question in terms of visual representation, then this is the representation of it. That image is X, we have this kind of regular structure, and with respect to network, the structure is kind of very irregular. Why? Because it's not like that. If I say this is my graph, then I'm saying that each pixel has exactly 1, 2, 3, 4 friends. But do you see that on Facebook, everyone with, let's say, fixed number of friends, let's say 100 friends? No, it's not like that. Everyone will have different number of friends based on his or her interests, availability, right? So many factors are there, right? Okay. So that's the difference between these two. Okay, but I guess before talking about other things, I must first answer the question which I have asked you. Okay, so let me kind of give you intuition about it, and then I will continue with my talk. So unfortunately, this we can't do, right? This is not possible. Why? Let me give you simplest kind of solution for it. Do agree that even if, okay, so this was one graph for which we had constructed one kind of adjacency matrix, and the idea was we'll give this to our neural network and we will get the answer. But now I'm giving one more, I'm taking one more graph, and you can see both of them are same graph, right? This is also representing the same graph G only, okay? But let me call it G dash. And this time I am labeling it differently. So what I will do, I will label this particular node as A. Let's say this node is B. This node is now, let's say, C, and this is D. C and D are remaining as it is, but let's say I will swap A and B. So if I do this, then what will happen with respect to my adjacency matrix? I have to change it. So let me quickly regenerate adjacency matrix for this G dash graph. Okay. So now again, I will write like this only. Let's say A, B, C, D, A, B, C, D. Okay. Diagonal entries are again 0 one more time. But now A is just connected with B. Rest of the entries of A are 0. And B is connected with C as well as D. So I can put like this. And now C and D are also connected. So I can put like this. So this is the matrix for G dash. Now, what can you say? Whether matrix written in black is same as matrix written in red, or they are different? Of course, they are different. I can read this and I can read this. This is 0 1 1 1. This is 0 1 0 0. So both are different. So that means if I give you, if I give G, okay, so let me use black font for G. If I give G to my neural network, okay, ANN, and then I get some result, versus if I give G dash to my ANN, okay, and G means I'm talking about adjacency matrix of G, and this is adjacency matrix of G dash, and then I get some result, let's say R dash. Then R won't, R may not be equal to R dash. Why? Because my input has been changed. G is not AM of G is not equal to AM of G dash, right? And that's why it's not work. Why? Because G and G dash both are same graph. So what's the issue over here? That if my input change, even if you ignore this, then simply you can sense that my output depends upon input, right? Uh, how good our students will perform, that's a function of how good our input will be, how good we teach, how good resources will provide. Depending upon that, the results will vary with respect to students. The same thing is over here. If my input will change, my output will be different. Here, if we follow like this, where we just change our normal matrix with adjacency matrix, then the issue is there are n factorial different orderings possible with respect to graph labels, and with each different labels you will generate different adjacency matrix. So therefore n factorial, which is very big number, n factorial different adjacency matrix are possible just for the same graph, and this won't work, right? Because for all those n factorial graph, my ANN will give some different result, but I want my result to be consistent, because all of this n factorial are nothing but, they are nothing but just one structural representation, right? Which is our topologically, if we say, then all of them are representing the same structure, right? So that's why this won't work. So now let me give you some more insight. So do you agree that whatever function I will pick in my architecture of graph neural network, that will be independent of my node ordering? Right? This is a very important property, that whatever I am going to generate, it must be independent of node ordering. How my it must not depend upon how I'm going to label the nodes. Okay, that's what I got. Now let me give you one simple intuitive question, and hopefully all of you will be able to answer this particular question. So let me take one simple example. Let's take a cricket player, let's say KL Rahul, and let's say these are the scores of his last 10, let's say IPL matches. Okay, last 5 IPL matches. Let's say 15, 20, then let's say 20. One more time. Let's say let me take different numbers. So just to make sure that we get better insights. So let's say 15, 12, 10, and suddenly he scored, let's say 105. Okay, and then let's say some in one match, let's say he has scored 37. So now, which mathematical function should I use to get a result which does not depend upon match number. So let's say this is match number 1, this is match number 2, this is match number 3, match number 4, match number 5. Okay, fine. And I want one mathematical function at least which does not depend upon kind of ordering of it, right? So it doesn't matter whether I take match 5 first, then I perform some operation, then match 4, then match 1, then match 3, and then finally match 2. This result must be equal to like this: match 1, then match 2, then match 3, then match 4, then match 5, right? So you will be able to relate very easily, right? There are 5 factorial different orderings are possible, and those 5 factorial orderings are again aligned with our 5 or n factorial different representations of graph, right? So I got 2 answers, both of them are correct: mean, sum. Apart from that, mean, the mean is the most kind of intuitive. Average of, and usually when you talk about cricketers, they whenever as soon as the cricketer steps into the ground, right, people talk about average. It's nothing but it's a representation that how good the player is on an average, how many runs he's going to score, he or she is going to score, right? So average of last 5 innings, it does not matter, right, whether you pick fifth match first or first match first, the answer will be the same. Apart from average, anything else? Apart from average and sum, any other function which you can recommend me? So as soon as we are going to use average, we can commit that node ordering is out of the picture now, because irrespective of I pick property of node 1 or property of node 2 or property of node 3 versus property of node 3 first and then 2 first and then 1 first, my answer will remain as it is. That variance is fine, but the common ones apart from average, in usually you use these functions many times. Extremes, right? Sum, mode, mean. Apart from this 3, more intuitive or easy, I can say. Range, okay. But before even range, you can talk about endpoints of range, right? Which are nothing but our minimum and maximum. These are also uh, famously, right? All of these functions, right? Whatever we have discussed so far, they are known as aggregation function. You hear this word many times in computer science, right? Aggregate means you combine data, but you are combining in a sense that ordering does not matter, right? So particularly with respect to graph neural network, the first function is extremely important to average, and the first model of graph neural network, which is called graph convolution neural network, uses this idea of averaging. Okay, fine. Okay, so let's continue. Let me give you some concrete examples also, so that you can motivate, so that I can motivate you for this particular field. So quick details. We are going to kill this entire process of feature engineering, which was there in machine learning. So instead of feature engineering, we are going to introduce representation learning. So what's the idea? That we are going to create one kind of vector representation for each of the node. Okay, so what we are going to do now? Okay, so now in the remaining time, I will give you the overall idea of the entire architecture, and then in the next class, I will cover it formally. So let me give you the entire idea how this graph convolution neural network works. So the first thing is we have this kind of idea of vector representation. So what this particular vector will represent, it will kind of consider not only the features. So let's say features of this particular node are A, but we are also going to aggregate features from its neighborhood, right? So let's say feature of all the neighborhood of A. So let's say this is, I can use this normal terminology. Let's say person 1, or maybe friend 1, friend 2, friend 3, friend 4. And then I'm going to take average of something, right? Average of their features, right? So let me say it concretely. And then I will also capture it. Okay. And not only this, I will go even one more step, and I will consider features of friends also. And then finally I will come up with some representation, and that representation will solve everything. Okay, so let me give you one simplistic example so that you can relate with this entire process. So let's say traditionally if let's say machine learning model wants to hire someone, then what it will do, it will just consider the candidate and features of the candidate. Okay, so what we are going to do, let's say you are the CEO of the company, then you will call that particular candidate, you will see his or her CV and all the credential, you will measure the performance of the person at the time of interview, and based on that you will decide, okay, whether that particular person must be hired or not. That's it. That's the machine learning model will do with respect to let's say selection or rejection of a person. Now, let's say I want to do the same process, but this time I'm going to use graph convolution neural network. Then what graph convolution neural network will do it is, let's say you are CEO of the same firm, but you are following graph convolution neural network based, let's say, strategy of hiring. Then what you will do, you will first conduct interview of the candidate, and you will give some score, and let's say you are going to give 80% importance to this score, whatever the person has performed in the exam, as well as based on his or her CV and credentials, whatever the criteria is, but you give only 80% importance to that particular criteria. Then you will also conduct interview of his or her friends. So let's say these five are his friends, and you will conduct their interview also. Let's say you have time, so time is not an issue, and you give, let's say, 15% importance to what they are talking about him, right? Right? So that is like that. And or maybe you also give some importance to what their credentials are, right? Like that. And then remaining 5% importance you give to, right, their friends of friends. And then you close this process, right? Based on this, you calculate the final score, 80% to performance of the candidate, 15% to what his friends are, what their credentials are, and what they are talking about this particular person, and then remaining 5% to friends of friends. And why we are not going even further, why we are stopping over here? Can you recall what with what portion of my talk you can relate this stopping criteria? I could go on and on. Why I'm stopping only at layer 2? I can go to up to layer 7, 8, 9, 10, 15, 20, 25, and then accordingly I can modify these weights, right? Because of course, by this time you will be able to guess that this weights will be given by nothing but this will be learned by our neural network, right? So I'm not worried about this weights, that how much importance to give to a person or his friends and friends of friends. So that will be learned by neural network. But my question is, why we are stopping like this? Why we are not going more than 2 to 3 hopes? We can this formally this kind of construction is known as computational graph. But do you agree that in the second method of selection or conducting interview, we get better insights, because not only I'm communicating with the person, but I'm also communicating it with his friends, and that may give me some insights. Do you agree? Right? So that's the whole idea of graph convolution neural network, that you do not only consider the points, but you also consider its neighborhood. And here we are going to apply that aggregation function, which is nothing but in this particular case, average. You're going to average the features of the neighborhood, and then you will repeat the same idea with respect to friends of friends also. But can you name the property because of which we are stopping at layer 2 to 3 only? The name of the property is, can I say it's small world property? Because small world property says by by the time you reach to 6 to 7 layers, you will be able to cover the entire graph. Because on an average, every dot is connected with every other dot with this distance. So if you stop too far, then effectively for just to give result for one candidate, you are going to conduct interview of the entire class, which doesn't make any sense. So that's why in this architecture, we usually stop very early, like up to we go up to only 2 to 3 hops, and then we give our final decision, right? So that's why that first discussion was important, and that's why the length of this computational graph, right? Formally, it's called computational graph, using which we will be able to kind of generate this kind of representation, right? the length of this computational graph is, that's why very small. Okay, fine. So if I continue, just a second. Okay, fine. This is fine. Okay. So now, up to this point, I guess we have discussed all of this. Okay, we'll talk about this. This is also done. Okay, and this was the main idea, how to come up with this kind of representation learning, right? So that we can kind of capture all the properties of the node as well as its neighborhood, right? In just one vector representation. So that's the entire focus now. So we are going to kill this edges now just by considering what it offers us, right? So if again everything will come back into will be mapped into vector space. So we are going to have this kind of vectors which will give us all the insights about the underlying data point, right? And all this different type of task I've already talked about. Node level, which is nothing but classification. Community level, right? Whether the like-minded dot points are together or not, and if they are, then we declare them as community. Edge level, prediction of whether two dots will be connected in future or not, right? So if I give some concrete examples, right? So they are mentioned over here. I have already explained them, so I'm not wasting time over here, right? And there are many applications. So I will be motivating you with two big applications with which I hope all of you will be able to relate very easily. And then I will give some primary. Of course, I have already talked briefly about architecture, but some concrete details I will give. One more time, we will revisit that particular justification why we can't use adjacency matrix, and then we conclude today's session. So that will be the flow. So the first application which I would like to highlight is protein folding problem. It's a very important problem in the domain of biology, because if you can identify the underlying 3D structure of protein within human body, then you will be able to cure a lot of diseases. Right? Biologists will be able to cure a lot of diseases if they can predict the human body protein 3D structure, right? So now, thanks to graph neural network, this problem is very close to be solved, right? We can't say it's completely solved, but we are getting very good results thanks to graph neural network, right? So as you can see, the experimental results are highlighted in green color, and the computational result which are obtained with the help of the proposed model of DeepMind, which is AlphaFold, again variation of graph neural network. You can see the kind of predictions. The blue line is very much matching with green line, right? And it's a very important, one can say, achievement, and it has gained a lot of kind of headlines. And well, people say it's AI, but of course it's a graph neural network. So usually we use AI as a generic term for all kinds of models. So of course this is one sub branch of nothing but deep learning, and deep learning is sub branch of machine learning, and machine learning is sub branch of again AI. So therefore one can say it's AI again. But if we are specific, then it's nothing but we say this specifically, then again it's nothing but graph neural network. And you can see, as compared to other state of the art methods, this AlphaFold, right, it's offering a very kind of, one can say, better results, significantly better results as compared to, right? So you can see, so up to this point, right, the progress was there, 40% GDT score, and AlphaFold 2 is offering around 90, right? So which is a tremendous achievement, one can say. And it's very likely that even in future, the Nobel Prize will be awarded for this work. And I'm not going into the details of this, of course, it's out of the scope, but just to give you insights how they are constructing the graph, because that's the important thing. So as you can see, nodes are nothing but amino acids in the protein sequence, and edges will be constructed based on how close in physical proximity the underlying amino acids are. And based on that, this criteria, that closeness criteria, the ages are considered, and you can see that finally they are doing this work. And with respect to recommender system, I've already given a lot of examples, so I'm not wasting time over here. But that's age level task. You are viewing this particular image, that and app suggests this, then it's fine. But if app suggests this, then we will say it's a bad app. Don't download this kind of app, right? Side effect of drugs, right? So this is again one more interesting problem, and graph neural network can save a lot of time in this particular case also, because if you even consider, let's say, many patients take more than 20 drugs. So even if pick let's say this 20 as my fixed number, and potentially how many drugs, I'm not talking about the 31st December type of drugs, I'm talking about drugs which are good, which cure diseases. So let's say even if I keep my sample space around 10,000, so let's say 10,000 different medicines are there, and which out of this 10,000, there are many patients who are taking 20 of them together. So this many different combinations will be there. And for each combination, I have to ensure that there are no side effects. That some side effects may even kill the patient. So we have to be very sure, because the side effects can harm patients in short or long run, right? So if we don't use this kind of models, then this kind of experiments can take many lives of volunteers, right? So how to resolve this, right? So again, you can represent drugs as well as proteins in terms of nodes, and ages are based on nothing but how this proteins are interacting with each other, as well as how which drugs will interact with which proteins. And I'm not going into the details that how so of course you can go back and calculate this number, right? Even if you will be able to estimate the difficulty of this particular problem, and you can see this 10 side effects have been kind of predicted by graph neural network, and the red ones are the ones for which actually the medical evidence are available, the literature evidence are available that this side effects are actually correct. So that means that showcase that whatever predictions has been done by kind of graph neural network models, they are actually valid in this particular problem statement, right? And I will motivate you with one more important example, which I guess all of us have used at least once in our life, which is nothing but Google Maps. In their latest update in, I guess, 2000, since 2024 onwards, they have implemented graph neural network in their model. And why they are using it? For improving the prediction of ETA. ETA stands for estimated time of arrival, right? So we use maps for two reasons. One, to get direction, and especially in the case of Google Maps, we also use to sometimes, at least I use it to just to know that how much time is required to reach to point A to point B. I very well know the directions, but ETA is also equally important, right? Because it will help us to schedule the rest of the day for us, right? And we can get the upcoming, we can schedule the upcoming tasks depending upon this kind of duration, right? Which the transportation or the tour is going to take, right? Or ride is going to take. So now, how they are using it? So they have used road as a network, right? Road network they have represented in terms of graph. So nodes are nothing but segments, and if roads are connected, then they are going to put edges between them, and then they have a lot of features associated with this road segments. Of course, we are not going into the details, but the idea is they are using it, and you can, if you are interested, I will share the resources. You can read more about this. This is just to showcase you that the domain, the graph neural network is kind of very much used in our day-to-day life, but still it's kind of underrepresented in the research community, right? So that is that. Okay, fine. So I guess I can read some comments like thanks. So maybe I guess I have taken slightly more time. So it's fine. I have one more hour. So if you want me to stop now, it's fine. We can continue this in the second talk also, because I have one more hour in which I will start from this node embeddings. So I will just, let me just complete with this one idea, and then the rest of the things we'll talk in the next class. So the idea is, as you can see, the red dots are very kind of close. The green dots are also very close. So we have to ensure that they are similar, right, in some nature, in terms of degree also, that you can see that this dots are having the same degree, which is kind of 2. This one is having 3. This one is also having kind of close proximity. So therefore, the color is kind of same. Color may also represent that, let's say this 4 students have got same grade, let's say grade BC. These are the toppers, they have got A grade, something like that. And now, when we do this kind of mapping in terms of vectors, we have to ensure that whatever kind of results we get in terms of this vector representations, those vectors are also close by, right? This we have to ensure. Otherwise, there is no use of mapping, right? If I map this student who has got BC grade with student who has got A grade, then my entire model will fail. Do you understand what I'm trying to say? That we have to ensure that whatever model we are going to design, that model captures all the structural property, all the essential aspects of the existing kind of representation, which is nothing but in this particular case graph representation. So not only we have to kind of capture. So if I write it down concretely, so what I'm trying to capture as of now is I'm trying to capture properties of the node, right? What are the properties of the node? That is important. I can't ignore it. Properties of node is important. Not only this, properties of neighborhood of, let's say node is node X, let me call it. Then properties of neighborhood of node X is important. Also property of neighborhood of node X is also important, because I'm going to capture it also, right? So these things we have already seen, because in the previous diagram, if you can recall, even though it's informal, but I told you that we are going up to 2 layers. So this is node, it's neighborhood of neighborhood. So all of this we are kind of capturing. And in this 2 case, we are going to take average. That is fine. But apart from that, I'm also saying that you also have to kind of capture topology of the original graph or original given structure, right? So that is also equally important, and we have to ensure that all of this kind of being captured in what representation learning. So too many things are there which we have to cover with this one simple solution, which is nothing but one vector of d dimension, and this vector will capture all of these things in numbers, right? So that's the intuition. That's the kind of idea of uh, graph neural network. So we are killing the entire field of that feature engineering, right? So everything will be kind of captured in this representation, and we call this vectors as nothing but. Of course, don't worry about how it's work actually, because that I will cover it in subsequent session also. Just a second. Okay, so don't worry. I guess I have one more session on, if I'm not wrong, on I guess Tuesday. Am I right, Dr. Vikas? So then I will cover the rest of the things. I will cover the rest of the things on Tuesday. Don't worry, right? So at least you got the motivation. That was the objective of this first session. We'll revisit this details in the next session. Thank you. If you have any questions, you can just email me. I am just writing down my email address over here because we are running out of time. So it's okay. You can in between email me. I will cover those things in the next session. Okay, fine. Thank you.
Thank you, sir. Thank you for this wonderful session, sir. Thank you very much for coming and accepting our invitation. Thank you very much, sir.
Thank you. Thank you, Surendra sir. Thank you.
Yes, sir. So the next session is on Tuesday, and the timing is still the same, 6 to 7.